So thanks to Vlada and Mick for the invitation. However, I have to tell you that when I was asked to speak to this small class, I was told there would only be 12 people in the room. So you understand I've prepared a presentation for 12 people, so I hope there will be at least 12 of you who will find it interesting. But I've also been asked to talk to you about mechanisms of continental glaciation, as these have appeared in the past, and maybe make some comments about the possible connections of continental glaciation to the biosphere and to climate, basically climate processes in general. And it's really the connection to climate processes in general that I'm going to focus on here. First, this picture is a good starting point, I think, because it actually places in time the three major periods in the last billion years of Earth history. That is, from the beginning of the Neoproterozoic, a gigayear ago, up to the present. During this period of time, there have been three main intervals in which intense glaciation has occurred on the surface of the planet. The first, of course, in the Neoproterozoic, where the now famous or infamous among many of us snowball events are supposed to have occurred. There is then later in time in the Carboniferous, around 300 million years ago, a very intense glaciation that occurred on the supercontinent of Pangaea, which at that time was located very near the South Magnetic Pole. And then finally, of course, this major era of glaciation, which we are just at the end of now. In fact, we're now just going into, as I'll argue, an intense period of final deglaciation of the planet during the so-called Anthropocene, when the increase of carbon dioxide in the atmosphere, which we're producing by burning fossil fuels, is beginning to lead to the complete deglaciation, perhaps, of the major continental or accumulations of land ice that currently exist at the poles. One of the, or the time series, which is shown in this first graphic, of course, is the isotopic variability of carbon, that is the ratio of carbon-13 to carbon-12, as a function of time measured basically in carbonaceous rocks on land, as a function of time during this period. And this isotopic ratio, of course, is extremely important because it's basically a measure of photosynthetic activity, as inferred on the basis of the inference from it of the increase in burial of organic matter that occurs as a function of time. And of course, this is clearly dependent on the fact that the process of photosynthesis fractionates mass. That is, whenever photosynthesis occurs, driven by input of photonic energy to the system, the carbonaceous material, the organic material that's generated in photosynthesis, is enriched in the lighter of the two isotopes, stable isotopes of carbon, carbon-12. And so this is the basis of the interpretation of increases in the del13C ratio, of an increase in the burial of organic matter on land, right, or on the surface of the ocean rather, okay, as the evolution of the climate system proceeds. So this is a very important connection, if you like, between climate variability in general, right, and life. Let's now take apart that picture and begin moving forward in time to the Phanerozoic, beginning basically with the Cambrian explosion of life, which began around 543 million years ago. And you will notice in this diagram that this, of course, is a time of basically super exponential proliferation of biological diversification. This is probably, in terms of Earth history, the most important connection between climate and life that has ever occurred on the surface of the planet. And I want to draw your attention to the fact that in this upper diagram, there is clearly also a very deep connection, as inferred on the basis of Bob Berner's work, and we can argue about that, and perhaps that's necessary, right, of a reconstruction of the variation of atmospheric carbon dioxide through time, which starts high at the beginning of the Phanerozoic, dips to a value near modern in the Carboniferous, which is the time of the deep glaciation that was experienced by Pangaea. With the breakup of the Pangaean supercontinent, there is a rise of atmospheric carbon dioxide according to Bob's reconstruction, and then a fall back to the modern level. Let me go back again to the next but last slide and draw your attention again to the dynamical processes which accompanied this sequence of glaciation events, and remind you of the connection between the supercontinent cycle and the occurrence of these periods of deep glaciation. For example, during the Neoproterozoic, when these snowball events are supposed to have occurred with very intense glaciation on a supercontinent located basically on the equator, this is a time in which the supercontinent of Rodinia, having been fully assembled by about 800 million years ago, began to break up, right? This then was followed by the assembly of the supercontinent of Pangaea, eventually found during the Carboniferous near the South Magnetic Pole, followed by its breakup. And let me draw your attention again to this diagram. Remember, here is Pangaea. Pangaea breaks up, and again, a rapid increase in carbon dioxide in the atmosphere associated with the breakup. Not at all unreasonable, because that breakup process would have been accompanied by intense volcanic activity, as most probably almost certainly would have occurred as well, accompanying the breakup of Rodinia. So Rodinia breaks up, huge pulse of carbon dioxide at the beginning of the Cambrian, right? Growth of vascular plants, other activity on the continents, drawdown of CO2 into the Cambrian, assembly of Pangaea, breakup of Pangaea, huge pulse again of carbon dioxide into the atmosphere, all accompanied in this sequence of events across the boundary of the Cambrian explosion of life, okay, by this massive proliferation of biological diversification. On the right-hand side now, connecting through the Phanerozoic eon, the occurrence of these most recent two events of massive glaciation with the low CO2 level in the Cambrian, basically a level about equal to modern, and then during the most recent episode of glaciation, beginning around 30 million years ago, right, with the growth of ice on the East Antarctic continent, following its split from the initial landmass that it was connected to, which is now South America, and basically the opening of Drake Passage. Let me blow up this further section of this diagram and look just now at the Cenozoic. So here is the growth of the Antarctic ice sheet beginning on East Antarctica around 30 million years ago. Here is the Paleocene-Eocene thermal maximum around 55 million years ago, which is much discussed in the literature now, a hot period rather than a cold period. Here is the growth of northern hemisphere ice sheets. Greenland, for example, had no ice on its surface until after about 3 million years before present, right? Until the end of the Pliocene, then Greenland begins to glaciate. This now snippet of time is blown up further in the period from 3.5 million years ago until now. This period of 3.5 million years ago is basically mid-Pliocene time, and I've pointed to this time 3 million years ago, which of course is a huge focus in the climate dynamic community with an international program called PLIOMIP, because if you go back to the picture of CO2 variations, you'll understand that the reconstructions of CO2 level during the mid-Pliocene show it to have been about 400 ppmv by volume, which is a number that we're just crossing or just have crossed, right? So this Pliocene time is a time in which many are imagining, whether this imagination is warranted or not is an issue, but where many people are imagining that the Earth must have been like what it is expected to be like in the next few, perhaps hundreds of years of Earth history. And finally at the bottom, and this will really be the takeoff point for the main body of information in the lecture. So this is a blow-up of the last 400,000 years of Earth history, which is dominated by these basically 100,000 year spaced variations in continental ice cover, mostly, as I'll argue, in the northern hemisphere, dropping till about 26,000 years ago to the time of last glacial maximum. So the material I've shown you to this point basically has gone from Neoproterozoic to now. Of course, the glaciation that has occurred most recently is the one which we understand best. So I'm going forward now, right? I'm going to start with a much more detailed discussion of last glacial maximum, of the process of quasi-oscillatory glaciation that has dominated Earth system history for about the last 900,000 years, and then moved back into the past using more refined models to actually address the question as to what we can say in detail about each of these glaciation events, and really in the process to try and argue the case for the deep interconnections between the climate of the Earth, as represented here by a picture based on a reconstruction of surface conditions at the last glacial maximum, right, during which we have this massive variation of sea ice cover in the northern hemisphere, when the northern hemisphere is covered by these massive accumulations of land ice, so massive in fact that global sea level at this LGM time about 26,000 years ago was down on average by between 120 and 130 meters. So to give you an understanding or some sense of what a huge impact this was in the Earth system, I'll tell you that the thickness of ice to the west of present-day Hudson Bay at that time was over 4 kilometers, between 4 and 5 kilometers. So this is a massive shift of mass out of the oceans onto the surface of the continents. And as I showed you in the previous slide, this massive shift, these massive shifts of mass from ocean to land have been an indelible feature and a quasi-metronomic feature of the Earth system for the last roughly 900,000 years of Earth history. The ice masses come to the continents, they deglaciate, they come to the continents again, they deglaciate. And I want to talk to you as we move forward as well about the physical process which is responsible for this, but this is going to require that we think very deeply about the connections between what's happening on land and atmosphere and oceans, the ocean components of the climate system, and deep Earth processes. So I want to try to argue in a way as to convince you that if we really wish to acquire a deep understanding of these processes, we cannot simply focus on atmosphere, on oceans, right, on the hydrospheric components of the Earth system, but we really have also to try to deeply understand their connections to deep Earth processes. So this is the order of march going forward. So I'm going to talk to you in detail now about the late Cenozoic, right? The last 65 million years of Earth history, focusing primarily on the last million years of Earth history. I'm then going to go and talk to you about the Carboniferous glaciation of Pangaea, and then finally make a few comments, at least one or two of which will be, let's say, points of discussion, okay? Because I'm going to introduce a new idea that could have been important during the Neoproterozoic, but I'm not going to be able to defend it in much mathematical detail. And I want to stress the different mechanisms at play in each of these different intervals of time, because each of these eras of glaciation appear to be controlled by what I call a somewhat different recipe, if you like, for the glaciation process. Different processes seem to have been more important than others during each of these periods of time. So let's start with the ice ages of the late Cenozoic. And I'm going to make use for 2 or 3 slides of graphics from the not the most recent IPCC report, but from the 4th assessment report. Okay, so here's the picture basically of LGM Earth with its distribution of continental ice masses in the northern hemisphere, and with the prediction of a modern climate model from a modern climate model as to what surface temperature would have looked like at that time. And as I'll show you, down on average by about 5 degrees C, integrated over the entire surface of the planet. So you might imagine this to be a relatively modest drop, if you like, in mean surface temperature. Okay, so this is last glacial maximum when the Earth looked like this. Okay. These are the variations of the 3 main greenhouse gases, carbon dioxide, methane, and nitrous oxide, inferred on the basis of data from the Vostok ice core, which is basically, I would say, a data set that's absolutely revolutionized our understanding, geophysical understanding actually, of the way in which the planet has functioned. I mean, it's almost a miracle. It's almost a miracle that the planet has conspired to remember, in detail and with high accuracy what the concentrations of the main greenhouse gases, which have driven variations in its climate over the past now basically 1 million years of Earth history. This is an enormous advance, I think, in understanding of the geophysical world. So what you can see is happening from Vostok is that last glacial maximum was a minimum, if you like, of all of the 3 main greenhouse gases, with carbon dioxide concentration, the main greenhouse gas, down to about, let's say, 180 parts per million by volume. Remember, today we're now up at around 400 parts per million by volume, and this shows you just how dramatic, from the ice core record, the rise in all of these greenhouse gases has been, like a delta function. Right, beginning with the onset of Northern Hemisphere industrialization around 1850, let's say, right? Totally unprecedented. So if we stretch the time scale again, looking at the full Vostok record and focusing just for the moment on CO2 in red, okay, you can see this almost metronomic 100,000-year quasi-cyclic variation. And what you must imagine in CO2, and what you must imagine is that picture of Northern Hemisphere ice cover basically blinking synchronously with the CO2 variations. But you must not imagine that blinking in a quasi-synchronous fashion with the CO2 variations is actually driven by the CO2 variations, which it is not, as I'll argue, because carbon dioxide in this ice age cycle, this 100,000-year ice age cycle, is really acting like a feedback rather than what I would call a prime mover of the process. Okay? But again, this blows up the full Holocene, going back 10,000 years before present, the time by which the system had totally relieved itself of the continental ice cover that was characteristic of the last glacial maximum. So, of course, the fundamental driver of this process has been known for a very long time to be the process which was first suggested by Milankovic going back to 1940 or so. And until about 1967, in fact, I'd put a precise date on it, this process was considered to be widely in disrepute. It was not seen to be a respected contribution to the scientific community at all. And his idea, of course, was that because of the small variations in the different geometrical elements that control the geometry of Earth's orbit around the Sun, which are associated with gravitational n-body effects in the solar system, the fact that the Earth and Sun are not alone, so the Earth doesn't simply execute a clean Keplerian ellipse, time-invariant Keplerian ellipse in its orbit around the Sun, but that ellipse is continuously wiggled with its eccentricity varying most strongly on a timescale of 100 kiloyears with an additional 400 kiloyear component. and with the obliquity of the spin axis with the plane of the ecliptic, that's the angle that the spin axis makes with that plane, right? With that angle varying on a time scale of 41,000 years, that the combination of this variation of obliquity and eccentricity in combination with the precession of the equinoxes, right, produces a variation in received insolation as a function of latitude on the surface of the planet, which is such that every roughly 100,000 years there is a massive negative anomaly in received solar insolation at high latitude, which triggers the onset of the glaciation process. These are the conventional variations in the orbital elements, just to draw your attention to how large this negative anomaly in solar in received insolation was at the time of the beginning of the most recent 100,000 year cycle in global glaciation. This is about 60 watts per square meter near the pole. This is a huge anomaly, right? And so what happens during the time, which is thousands of years during which this anomaly is maintained, this is a time in which summers are so cold that we're unable to melt all of the snow that accumulated at high latitude during the previous winter. This anomalous balance is held in place for a period of thousands of years, allowing a massive accumulation of snow to develop, which compacts under its own weight to make ice, which begins to flow over the landscape and produce ultimately, at the end of the glaciation phase of the 100,000 year cycle, to correspond to this drop in mean sea level on the planet, which is between 120 and 130 meters per year. But I've made the point that although this 100,000 year cycle, right, cannot be imagined to be forced by the CO2 variation, which occurs perfectly in phase with it, the CO2 variation must be understood to be a feedback operating in the system, which especially assists in the deglaciation phase of each of these 100,000 year cyclic variations of ice cover. So I want to show you how this works, and this is sort of a conventional now mathematical incarnation of those words, okay? So we take a fairly simple but nevertheless highly nonlinear representation of the accumulation through an accumulation function, right, of ice on the surface of the continent, and describe the evolution of the thickness of this ice as a function of time in terms of a nonlinear diffusion equation on the surface of the sphere. Okay? Nonlinear because the process which in which, under the action of the gravitational field, ice is forced to flow over the surface on which it sits, with a diffusion coefficient, which is a very highly nonlinear function of ice thickness and ice thickness gradients, horizontal variations of ice thickness. Okay? So we couple in this model this highly nonlinear diffusion equation with an effective viscosity, which is a basically thermally activated process which has a well-determined activation energy. So it has a viscosity through this factor A, which is a strong function of temperature. And we connect that nonlinear diffusion equation for another nonlinear diffusion equation which describes the surface energy balance of the climate. And here I'm using Jerry North's model, which is still, so far as I understand, the best available energy balance model of surface temperature variability. It's one that resolves the continents and the oceans. It's one that explains the amplitude and phase of the annual cycle as it varies over the surface of the Earth. It captures all of those physical processes. And a third physical process which is linked in this model is a very simple representation, at least the results I'll show you use this very simple representation of the isostatic adjustment process. When you put a huge mass load on the surface of the Earth and maintain it on a long time scale, of course the Earth eventually sinks under the weight of the load, right? And on a very long time scale, of course, the solid of which the outer part of the Earth is comprised begins to flow like a liquid with a viscosity that's extremely high, right, on the order of 10 to the 20 or 10 to the 22 times the viscosity of water, but it nevertheless flows. Think of it as silly putty, right? And that load, which starts off as with a thickness above sea level of, let's say, 4 or 4.5 kilometers, eventually sinks into the Earth, deflects the surface of the solid Earth. Material flows out from under the loaded region, causing bulges to be produced around the ice load. And by lowering the surface of the ice-covered region, it basically brings the precipitation regime, if you like, to which the ice sheet is subject, into a different region of activity, i.e. the air above the ice sheet is no longer as cold as it would otherwise be. It's warmer, right, and therefore can hold more moisture and therefore can deliver more moisture to the ice sheet in the process of sustaining it. Okay, so here now is basically an animation, I hope, of the most recent 100,000-year Ice Age cycle based on a detailed integration of those coupled evolution equations using North's climate model to produce surface temperature variations and using our own model of land ice evolution over a full glacial cycle. Here we started off at 116 K when that first negative anomaly hits the northern part of the continent, of the North American continent. Here we're moving slowly up towards last glacial maximum around 26, 21 K. But you see that this ice sheet is a highly dynamical structure. It doesn't just grow monotonically up to its maximum and then collapse. It increases, decreases, increases, decreases in response to the oscillatory input that's basically coming from the variations in orbital insulation change. So here we're just moving up towards what in this model is LGM, okay, and now melting back. And you'll see very slowly how Hudson Bay is eventually formed. So the blue is always outboard of the ice, right, is always water, right? These are proglacial lakes which are well known to have surrounded the ice mass. And finally we end up with Hudson Bay in its current position. Now if we want to do a multi-cycle integration, basically to demonstrate that CO2 actually acts as a feedback, not as a prime mover, we nevertheless have to take into account this beautiful fact of the correlation between CO2 variability, okay, and oxygen isotopic, marine oxygen isotopic variability, right? This being proxy for ice volume, Shackleton 1967, a hugely important paper in all of this work. And you can see there's an almost perfect correlation, right? But the question is, should this be construed to be prime mover, or should it be understood to constitute feedback? Well, we can investigate that by running the model that I've just described to you over a much longer period of time. So we put into the model a synthetic CO2 record based on Vostok that takes us back, let's start at 650,000 years ago. We'll input 62 degrees north latitude, June, July, and August insolation. Okay? And we'll run the system forward, inferring on its basis, on the basis of the ice volume produced, the fall in sea level, right? Inverse oxygen isotopic ratio that would have been produced in the run, okay? And then we can take this record, do a simple power spectral analysis of that record, which is basically shown here, which mimics the Vostok history and the deep ocean history based on Del 18O perfectly. We get a strong spectral line with a period of 100,000 years. However, the input orbital variations, right, which come basically from reconstructions of the Earth's orbit around the Sun, has basically no power at this period of 100,000 years. So this is a highly nonlinear oscillation, which is triggered, that is, it's instigated by northern hemisphere low insolation anomaly that develops for orbital reasons on a timescale of approximately 100,000 years, but it's aided and abetted by the feedback associated with carbon dioxide variations. And I'll simply say that if we clip the CO2 input out of the forcing to the model, what happens is that we see a beautiful buildup of the glaciation phase of the cycle, but the deglaciation phase, the fast part of this relaxation oscillation, right, never goes to completion. It is the full deglaciation event of the cycle that requires the CO2 feedback. That's why I argue that the carbon dioxide is operating as a feedback rather than as a prime mover. If we open a window in this model, at last LGM, last glacial maximum, we see exactly how the ice sheet is known to have looked at that time. Okay? So even though the model is simple, it seems to capture the basic characteristics of the behavior of the physical system on that time scale. But of course, models like the one I've just used to show you the results of these analyses are really, really simple models. And what we'd like to do is actually see how far we can get in further understanding of this process by using modern coupled climate models which resolve all of the atmospheric processes that are pertinent, which resolve ocean dynamics, which include full influence of sea ice, all of that, and actually reconstruct the climate of these times, actually using models in this class rather than using models of the reduced complexity class that I've just shown you results from. So we're going to take now, in much of the material I'm going to discuss going forward, we're going to take a modern model of the coupled climate system, results of which are being shown here with evolving images of water vapor concentration in the atmosphere, with closed contours basically indicating individual rainout events, okay, right? And fully resolving in this particular region around Antarctica the continuous generation of cyclonic activity in the rain belt above the Antarctic circumpolar current. Okay? So these models now are models which include as much of the physical system as we think we understand, and what we want to do is to use them to attack the nature of climate at different times in the past in which glaciation processes have occurred. So this is a story now of what we need to do in order to reconstruct ice age climates. And the first issue, of course, we have to face is what are the boundary conditions, right? How do we know when we attempt to run a modern coupled climate model under glacial boundary conditions? For example, suppose we want to understand what the climate was like, all aspects of the climate were like, right, at the time of last glacial maximum. Well, we need to know what the variation of topography was over the surface of the planet. We need to know where the ice sheets were, because the albedo of these ice sheets is higher than the landmass which they now cover, right? We need to know what the concentrations of greenhouse gases were in the atmosphere at that time. Even if we're just after a snapshot, what was the climate like at the last maximum of glaciation? Not trying to solve a transient problem, but just trying to understand what climate conditions would have been like at this time. So the first part of this story is how you reconstruct the boundary conditions, and these boundary conditions are now universally derived by using this theoretical structure that I've developed over the past multiple decades, which is based upon a formal theory of the interaction of ice, solid earth, and oceans. So we need to understand how to predict in detail the variations, for example, of sea level that would have occurred over the surface of the earth due to the buildup of a given concentration of ice on land, right? And we have to do this in a fashion which is fully accurate so that we can defend in detail precisely what the topography was, where the ice accumulations were, how much ice there was, right? All of these aspects of the boundary conditions, right? Surface boundary conditions, we have to know, and we can learn these by applying this formal theory of the glacial isostatic adjustment process, which is a formal theory of ice, earth, ocean interactions, which follows this long story which is still continuing on the formal side. So the inputs to this theory, if we wish, for example, to understand what the boundary conditions must have been like at the last maximum of glaciation, consist in part of a very large number. I have something of order 500 to 800 time series of this sort, and I'll show you more examples of this momentarily, of the history of relative sea level change at all of these locations over the Earth's surface, right, from the time of the last maximum of glaciation up until the present. So for example, if you look at an example of these relative sea level histories at a place like the southeast corner of Hudson Bay, which was covered by this huge thickness of land ice, what you'll see is that as a function of time beginning around 8,000 years ago when the land was first uncovered by ice, what you observe is a relative variation of sea level which falls, and it falls in an exponential, quasi-exponential fashion, at first very rapidly and then more and more slowly as a function of time. Similarly, over the Gulf of Bothnia, which was the center of a further accumulation of land ice in northwestern Europe, okay? And basically all over the surface of the Earth, we have these collections of radiocarbon dated relative sea level histories, which we can tune to sidereal time using the standard calibration of the radiocarbon timescale. So in order to infer what the variation of land ice was as a function of time, we have first of all to know where it was, and here is the picture of what northern hemisphere land ice was at the last maximum of glaciation. We then deglaciate it according to the carbon-dated deglaciation isochrones of the landmass on all of the continents that were ice-covered, and then using that formal theory we make a prediction of relative sea level history everywhere. And here is the prediction of the relative sea level history at the island of Barbados in the Caribbean Sea, originally Rick Fairbank's record, which is still basically the Rosetta Stone, I guess you'd call it, of this whole field, because it captures the entire variation of sea level from the last maximum of glaciation 24 to 26,000 years ago right up to the present, and shows this 120 to 130 meter rise in mean sea level. And as it happens, and as I've shown, this particular location actually measures the average. So if I were to compare the predicted history here to the history of the rise of mean sea level averaged over the entire surface of the oceans, I would get within 5% of the measurement that's made at Barbados. This is the reason why this data set in the complete collection of records of this kind is so important. Here is a basically demonstration of how well you do at a large number of locations over the Earth's surface. The model is tuned to fit the uplift histories at the centers of the regions which were once covered by large thicknesses of land ice. And then the theory is used to predict the variations that are observed basically everywhere else. And the quality of the fits that we achieve to these records is extremely high. So that's the way we get the surface boundary conditions. We know where the ice was. We know how thick it was. We know from the isostatic adjustment analysis what the elevation of the ice sheets were at the last glacial maximum relative to the sea level that existed at that time, right? We know the trace gas concentrations from the Vostok ice cores. We know what the orbital configuration was. We have everything we need in order to use a modern climate model to reconstruct basically ice age climate. So the first results I'm going to show you here are from the CCSM3 model. That's the model previous to the previous version of the NCAR model. And on Wednesday I'll be discussing new results from the Community Earth System model version 1, which is a much higher resolution model than the one I'm going to show you results from here for LGM climate. But I'm going to start by showing you a major output from this run of the coupled climate model. And this basically consists of the evolution of sea ice cover during comparing basically at LGM the annual cycle, pre-industrial annual cycle of sea ice cover, here on the left, with the variation of sea ice cover at last glacial maximum. And I want to draw your attention to the fact, right, that the southern boundary of sea ice extent during the winter, so this is a full annual cycle on each side of the diagram, right? You'll see that the southern boundary of sea ice extent at the last glacial maximum reaches as far south as the north coast of Spain, right? So this is a major impact of the dramatic cooling which occurred, if you like, at last glacial maximum time expressed in terms of sea ice. And this is basically what we're able to achieve in terms of the reconstruction of past climate states using a modern model of this process, if we know the boundary conditions. That's a static reconstruction, if you like. We do a snapshot analysis. We say, okay, we want to know what LGM was like. But what can we do in terms of a transient analysis, right? Can we say anything about the way in which the climate system must have evolved as a function of time at a particular time in the past when we know that dramatic events had occurred, okay? And here what I'm going to use is probably the most famous example, if you like, of rapid climate change, if you like, in the paleoclimatology literature. And this has to do with the explanation of the Younger Dryas cooling event, shown here in terms of sea level. So here's sea level history coming out of last glacial maximum, and the scale is reversed in sea level, right? So as we come out of the glacial, sea level is actually rising, and the scale is reversed here for clarity, so I can separate it basically from the temperature records. So what happens as you come out of the glacial is that there is a massive pulse of sea level that occurs coincidentally with what's called the Bowling-Allerod transition. It's a transition that follows what we call Heinrich Event 1, which consisted of a massive outflux of icebergs onto the North Atlantic Ocean through Hudson Strait off the eastern flank of the Laurentide ice sheet. These icebergs were continuously sent out into the North Atlantic, and as they traveled, got caught up in the North Atlantic drift, they melted and added a freshwater cap onto the surface of the North Atlantic Ocean, strongly inhibiting the deep water formation process in the Greenland, Iceland, Norwegian seas and the Labrador Sea. And this slowed down the thermal haline circulation. When this Heinrich event turned off, the thermal haline circulation revitalized, and I'll be showing this in detail on Wednesday. Okay? The system then began to cool slowly, and then finally, extremely rapidly, coming out of the glacial, the system cooled back towards basically full glacial conditions, stayed there for a time scale on the order of 1,000 years, and then rapidly recovered back into the Holocene conditions. So what we want to do here is to try to understand this event, right? Why did the system decide that it wanted to return to glacial conditions? Why did this last on the order of 1,000 years? What was the trigger that turned it on? And we want to use the same modern climate model to try to explain in great detail that process. So here's the setup. So the Younger Dryas, of course, is named by this famous 8-petaled flower, Dryas octopetala, right? Which was the basis on which the Younger Dryas was named. It was a flower that became prolific all over northwestern Europe at the time this event occurred. Obviously a cold-adapted species. The explanation, the standard explanation for the Younger Dryas, was the explanation produced by Wally Broecker going back now about 15 years ago. And Wally's idea was the following, that as this massive ice cover of the Laurentide ice sheet began to retreat in North America, it basically uncovered the present-day Great Lakes, which were filled proglacial lakes. And at that time, the glacial lake Agassiz, which was collected along the southwestern flank of the Laurentide ice sheet, had a route whereby it could flow to the sea, and that route took it basically to the east, fresh water to the east, out onto the Atlantic Ocean, through the present-day St. Lawrence River outlet. So Wally's idea was that the Great Lakes became uncovered by ice, right, at the time of onset of the Younger Dryas, around 12,800 years ago. The water that had been collected in all of these proglacial lakes squirted out to the east, covered the North Atlantic, Greenland, Iceland, Norwegian, and Labrador seas by a freshwater cap, turned off the thermohaline circulation, or at least turned it down significantly, decreasing the rate at which heat is released to the overlying atmosphere and cooling the entire hemisphere of the planet. Okay? So what we want to do now is, first of all, to ask the question, did the water actually move to the east? If not, where did it go? Right? And as I'll argue, it actually went to the north. But if it goes to the north, the question is, if it ends up in the Arctic Ocean, will it eventually have the same impact on the overturning circulation of the ocean as was expected to be the case when the outflow was to the east through the St. Lawrence River outlet? So this is a question we can answer using the same modern general circulation model which I've been employing up to now. First order of business, though, is to be able to answer the question, which way does the water go? Well, water flows downhill. I mean, that's my deepest understanding of hydrology. Okay? And so the question is, can we actually compute which way the water went? Okay? So this clearly requires that we understand the deglaciation isochrones, right, of the Laurentide ice sheet. And happily, we now, primarily through the efforts of Art Dyke at the Geological Survey of Canada, we have a very detailed map of the deglaciation isochrones for the Laurentide ice sheet. And it's exactly these deglaciation isochrones that I've used to constrain the time dependence of the variation of ice cover that's included in the glacial isostatic adjustment calculations. Okay? So if we know how the ice sheet is deglaciating in space through that range of time, we know how the thickness of ice as a function of place is changing. We know what the water load applied to the landscape at that time would have been, but the ice sheet model that we use to predict the variation in ice cover is one that has to be sufficiently complicated to encompass all of the variations in surface properties under the ice sheet that we know to have existed. Where was the bedrock outcrops? Crystalline basement. Where was the basement crystalline? Where was it sedimentary cover? Okay? Even that level of detail needs to be built into the deglaciation model. We then need, having produced for example, an isopac map for the thickness of ice at last glacial maximum, coming from the ice dynamics model I showed you previously, which we show to fit previous reconstructions of ice thickness based on geomorphological arguments, which show the existence of a dominant Keewatin dome of ice west of present-day Hudson Bay at that time. We need to take a realistic model, hydrologically rational model of topographic heights with respect to sea level, which are hydrologically corrected, so that we know if we rain on the modern landscape, the water always follows the right route to the sea, right? And since we have to operate at a lower level of resolution than would be required of a high-resolution modern-day model of surface hydrology, we have to make certain that all of the inhibitions, right, in all of the drainage network are matched to the resolution at which we can afford to run the hydrology model when it's fully coupled to the model of deglaciation. When we do this, the result we get, which was published in Nature in a paper with Lev Tarasov quite a while ago, is this result, right? So as a function of time beginning from 15,000 years ago, here's the Younger Dryas interval, okay? So initially, at meltwater pulse 1a time, basically all of the meltwater is flowing into the Gulf of Mexico. And if you look at the landscape of the American side of the border of the North American continent at this time, in particular if you fly over North Dakota at low level, as Wally and I and others have done, looking down, what you'll see are these huge, roughly kilometer-wide channels that were the meltwater channels, basically, that took the ice, the meltwater produced by the disintegrating ice from Western Canada through these meltwater channels into the Mississippi River network to the east, right? And then out onto the Gulf of Mexico. So the model predicts properly the appearance of meltwater pulse 1A in the Gulf of Mexico, exactly as Wally and others had argued, that that's where the meltwater went during meltwater pulse 1A time. But you can see what happens in this calculation is that as we move into the Younger Dryas interval, there's a switch in the runoff direction, and the switch in the runoff direction is from the south into the Gulf of Mexico to the north into the Arctic Ocean. Okay? So this is now the currently accepted explanation, actually, of the onset of the Younger Dryas, because it was verified by a group of scientists very recently who visited the Mackenzie River outlet into the Arctic Ocean, looked carefully at the stratigraphy of the landscape in that region, and found that during Younger Dryas onset time, there's a horizon in the sedimentary stratigraphy which consists of very large boulders indicating a high energetic outflow, which is bounded in carbon time, right? Precisely bounding in carbon time precisely the full Younger Dryas interval. So the full Younger Dryas interval, not just the startup, but the full 1,000-year interval of the Younger Dryas. A further calculation has now been done very recently, about 2 years ago, using the MIT GCM. And basically the analysis by this group, which was published in PNAS, basically showed that if the meltwater had gone out to the east, as Wally had originally imagined, actually it would have been trapped in boundary currents, in western boundary currents, and never made it up to the North Atlantic in such a way as to be able to shut down the thermohaline circulation and thereby explain the cooling. Whereas when the same model, the MIT GCM, was applied to the freshwater outlet into the Arctic hypothesis, the water got trapped, the fresh water was spun off of the Beaufort Gyre, advected to the east in the transpolar drift, down through Fram Strait, onto the Jin Seas, boom. There goes the Younger Dryas cooling event. So can we see this actually in a full modern coupled atmosphere ocean GCM? Well, all we need to do is to use the GIA reconstruction, the glacial icetic adjustment reconstruction, to make what the boundary conditions were at the time of the Younger Dryas, and you can see that they're almost full glacial, right? What had happened, of course, at that time was the development of a channel, an open corridor, as it's called, between the Cordilleran ice sheet to the west and the Laurentide ice sheet to the east. And many of you who will know something of anthropology, archaeology, etc., will know that the opening of this corridor was originally imagined to be one of the routes whereby Proto-North Americans could have made it into the core of the continent, right? At or around the time of the onset of the Younger Dryas. But for our purposes here, all we want to do is to spin up a modern atmosphere-ocean coupled GCM to answer the question, if we put the meltwater here, or if we put it here, does it make any difference insofar as the impact on the thermohaline circulation is concerned, and therefore can we discriminate between these different explanations, if you like, of the Younger Dryas based on the issue of where the water actually went. So what you discover in a standard coupled atmosphere ocean GCM is a very beautiful result, which is basically shown here in a paper by Guido Vetteretti and I that was published about 4 years ago, in which just a startup water hosing experiment in which we put, this is just a standard experiment where we put the fresh water in between 50 degrees north and 70 degrees north over the North Atlantic, and just ask what happens in detail. And that's basically shown here in terms of thermohaline circulation strength, where we, depending upon how many spheroids we hit the surface with in terms of fresh water, we diminish the intensity of the overturning circulation by differential amounts. Not surprising, okay? But the really beautiful result that we see in the cross sections here is that as a function of time following the imposition of the freshwater forcing, right, where we see at first a western boundary current, okay, a Gulf Stream, basically at the surface of the model. These are east-west cross sections. Below it, you see the deep western boundary undercurrent, which transports deep water from the regions where it's formed in the North Atlantic to the south. Okay? When we start freshwater forcing, of course, all that happens is that the deep western boundary undercurrent is turned off because we're not forming deep water in the north. But the Gulf Stream, of course, being wind-driven, continues to flow. Okay? So that simple atmosphere-ocean connectivity is fully captured by the model, leading credence to the sort of results that you can generate, basically doing full coupled atmosphere-ocean models of the attempts to answer the question as to whether it matters whether you put the freshwater load directly into the Atlantic or whether you put it into the Arctic. And basically the final result of these calculations is basically shown here, showing the results of Atlantic forcing and Arctic forcing. Whether you put the water in the Atlantic directly or whether you put it into the Arctic, the net impact on the strength of the thermohaline circulation is basically the same. But these models are not only good at explaining the impact on the thermohaline circulation, they also turn out to have high skill in explaining the depression of air temperature that you see in the Greenland ice core during the Younger Dryas event. Okay? And these data are basically from Jeff Severinghaus, Gratchev and Severinghaus, 2005, based on rare gas analyses in the ice core itself, which show the temperature depression in North Atlantic air being about 10 degrees centigrade. So these models are actually able to capture that, and they do so whether the fresh water goes directly into the Atlantic or whether it goes into the Arctic. And I've already presented the argument to you, not in detail, but the results from the MIT GCM, which basically say even if the fresh water had come out through the St. Lawrence River outlet, it could never have gotten into the North Atlantic because it would have been trapped in western boundary currents and moved to the south, rather than been caught up in the North Atlantic drift and moved up over the deep water formation regions. And of course the impacts on air temperature, of course, of the entire hemisphere are severe. Now I'm already an hour in, and I haven't told you anything about the Carboniferous yet. nor about the Neoproterozoic. So I'm open to suggestions as to whether I should shut down here or whether I can talk for another 10 minutes or so. I don't want to belabor the point.
If you can get to 10 minutes, go through some general...
I'll go quickly through a couple of general ideas and then stop and we can have questions. The Carboniferous part I can go through actually quite quickly because it stresses an especially important aspect of climate system dynamics as you move further and further back into the past. And that's the variation of solar constant, basically as a function of time. You know that the sun is a main sequence star. It burns ever brighter as it ages. The rate of increase of its output is at the rate of about 1% per 100 million years. That's standard astrophysical reconstruction of the evolution of main sequence stars. So as we move back into the Carboniferous, depending upon whose reconstruction you like, we've got a reduction of between 2.5 and 3.3% variations in the solar constant, right? So we need to reduce the solar output when we move back into the Carboniferous, and we need to ask then, what are we able to say about the glaciation of Pangaea, the Pangaean supercontinent, which existed near the South Magnetic Pole basically at that time. So here is basically I need to be careful here. So here is the reconstruction of Pangaea. This is all described in a paper with Bill Hyde and I and Tom Crowley I think Jerry North was on this paper with us as well. The red dots show the places where 300 million year old evidence exists for the presence of glacial diamict, indicating the presence of ice cover at that time. Here are, as I'll show you the reason, and I'll show you the reason for this, different times in the sampling of the model prediction of the extent of ice cover on Pangaea. Okay? So we use exactly the same energy balance coupled model of ice sheet evolution as I used to describe the most recent variation in ice cover, and I'll just show you a couple of results from this calculation. So we know that from Werner's reconstruction, we think that the CO2 level in Carboniferous time was modern. Okay? So here is the standard control prediction of the climate model, right? We spin up the ice cover on Pangaea, it oscillates, varying with variations in orbital configuration, which we cannot reconstruct accurately in phase, right? But we can reconstruct with reasonable confidence in terms of amplitude. We then, on this model, we rerun at twice the CO2 level, and this is the level of ice cover we predict. We triple the CO2 level and we get nothing. Okay? So these are just perturbation experiments on our ability to predict whether there should have been glaciation on that supercontinent. On this side, same perturbation experiment. We're now 3% down, basically in the output of the sun. Model spins up, produces oscillatory variations on a time scale. The length of this time series is much shorter than the one on the left. If we only turn down the forcing by somewhat less than 3%, okay, and then even less, okay, then if we had not turned down the forcing by at least 3%, we wouldn't have gotten any action at all. Okay? So in terms of the recipe for the glaciation of Pangaea, the argument is that you need both CO2 to be, if you know that CO2 is at modern, then you need a 3% reduction in the intensity of the sun in order to produce that glaciation, but that's the decrease in intensity which we have good reason to believe was the case. I can't really talk to you too much about Neoproterozoic snowballs because that would get me very, very deep into an extremely interesting issue, but I'm over time and I'll stop there. Thank you.
Beautiful, thank you very much. So please, this is a time to open the discussion, and I'm sure there's a lot of questions. Go ahead.
Okay.
Please.
I have a question. What is the role of the background albedo, and how the biosphere could affect these glacial cycles?
Yeah, I mean, of course, in the climate model, wherever we have ice cover, we of course must tune up the albedo. Okay, so the albedo variations associated with the glaciation-deglaciation process are built in, but those that would have accompanied variations in the biosphere, which undoubtedly had to have accompanied, right, the process of glaciation and deglaciation. For example, we know that during the last glacial maximum, the biome boundaries over the North American continent were strongly shifted to the south, and then during deglaciation they massively migrated back towards the north. So there are large biome boundary shifts that accompany the glaciation-deglaciation process, and there would be, how significant, I don't think we know, but there would have been clearly variations in surface albedo that would have accompanied those shifts in biome boundaries. I don't think anyone to my knowledge has really looked at this in detail, but it's a very interesting question.
It's going to be actually in 2 weeks' Tyler Gold from MIT, who's working a lot on how weathering rates are impacted by biology. He will talk about these processes. More questions? Mick?
I was wondering about the inception of the glaciations in the last million years.
Yes,
and,
yes.
This anomaly,
Yes.
the Milankovitch anomaly.
Yes.
could you comment on what happened prior to that? I mean, because the glaciation seems to be more frequent before that.
Yeah, they were undoubtedly, they were basically operating on a 41K timescale prior to about 900,000 years ago. So there was what we call the mid-Pleistocene climate transition, right, which occurred basically at that time. I mean, the explanation which I buy, and there are several out there, is actually the explanation which Barry Saltzman suggested in collaboration with Bob Berner, right, which follows from the fact that in terms of Del 18O, there's a clear indication that the system continuing to cool from the beginning of the Pleistocene, let's say around 2 million years ago, right, until that climate transition. And we would argue that that's basically driven by a continuous decrease in the mean level of CO2 in the atmosphere. That was basically Barry's suggestion, right? That cooling was associated with a continuing drawdown of CO2 in the atmosphere, which allowed ice sheets to expand to a larger scale and therefore to become more sensitive, if you like, as they climbed the insulation gradient while moving to the south. So we imagine that there is an increased fragility in the system as it becomes colder in response to the continuing decrease in CO2 level that allowed larger ice sheets to grow and begin to enter this highly nonlinear regime where, in spite of the fact that there's basically no power in the 100,000 year forcing, the nonlinearity allows the system to become sensitive to the modulation, right, of the precessional influence by the 100,000 year variation in eccentricity. And of course, this could never happen if the system were linear. So I see this as being, you know, the best clear demonstration we have of how nonlinear this process actually is. So a linear system could never see the modulation of 41K power, 22,000 year power by the 100,000 year variations if the system were simply linear.
Terry?
So you mentioned, Dick, earlier in the talk that these first two big periods of glaciation were
Yes.
accompanied by the formation of supercontinents.
Yes.
And that volcanism that might have accompanied the breakup of CO2 back in the
Yes,
atmosphere.
yes, yes.
But maybe you said it and I missed it. What then is responsible for the most recent glaciation in terms of this long decline of CO2 you were just talking about? What's driving that?
In terms of, well, this is
3
what.
million year, last 3 million years, something like that.
Well, I mean, again, if you look at the cooling curve, not the Keeling curve, the cooling curve. Sorry. Just based on benthic 4M Del 18O, which is basically imagined to be control on the overall temperature of the system, basically because the benthos basically sees deep water which is forming at the poles, and to the extent that that's becoming colder and colder, we imagine the entire system is cooling, right? That onset, for example, of northern hemisphere glaciation at least, the glaciation of Greenland, right, was associated with that overall cooling. However, the explanation for the onset of glaciation in Antarctica is considerably more complicated because it is observed to have occurred, subsequent to the opening of Drake Passage, for example, right? First you isolate it, and then it glaciates on the pole. But before it's isolated, it is not glaciated. So there's real complexity, I think, in the modern record about which we have the greatest degree of understanding.
I'm just puzzled, but maybe it's just a question of timescales, by the 3 million or 5 million year timescale drawdown of CO2. Where does that fit into?
Well, again, if you buy the argument, okay? So we start off with Pangaea on the South Magnetic Pole, right? Heavily glaciated. Pangaea breaks up, okay? The continental fragments are dispersed. Presumably there is intense volcanism associated with that. This is now imagination, and my arms are moving rapidly, okay? Right? And the atmosphere then is The atmospheric gun, if you like, is reloaded with CO2,
Yes.
right? And then the system begins to draw down that excess CO2 load in the atmosphere into the oceans. Okay? Right?
Okay.
And of course, this gets complicated because the ability of the oceans to draw down that CO2 depend on these long timescales on continental weathering effects and all of that, right? So all we can say, I think, right, is that following the breakup of Pangaea, right, CO2 began to fall in a quasi-monotonic fashion, right, towards, and it was exactly, that would be the argument, yes. I mean, that's the way my arms are waving. That's my story, and I'm going to stick to it until I'm shown that it's totally ridiculous. But it seems rational to me to think of this process of supercontinent creation and destruction as being associated with a very strong modulation of the atmospheric CO2 level. And that's one of the reasons why I like, in spite of myself in many ways, the Berner's reconstruction, right? Because I see it as connected to the same process, but with the supercontinent of Rodinia rather than the supercontinent of Pangaea. It seems to be all of a piece.
How do you reconcile your simulations of the Younger Dryas with sea level fingerprints, which indicate that Antarctica played a significant role in meltwater pulse window?
Let me roll this back. So now you're talking about something about, I think you're talking about apples when I'm talking about oranges, but first on the issue of meltwater pulse 1A, okay? In the recent reconstruction, which is just coming out in JGR Red, long reconstruction which is for the ICE 6G _C VM5A model, okay? There is a contribution to meltwater pulse 1A from Antarctica, and that's based on the results of Weber and others, right, which show in a region which they refer to as the valley, the evidence for massive iceberg flux coming off Antarctica at meltwater pulse 1A time. But that, the contribution, of course, of that iceberg flux to sea level is really a question, you know, how much actually involves sea level. I think that it was associated with the release of ice from regions around the shelf where the ice was only moderately thick and could be lifted off the shelf by the large contribution to meltwater pulse 1A coming from the Lorentz ice sheet. Okay? Because, as you know, in the gravitationally self-consistent theory, when you melt down the ice in the northern hemisphere, sea level rises most rapidly in the south. So there must have been a reaction in terms of Antarctic ice cover to the meltwater pulse 1A flux into the Gulf of Mexico, which is well known, of course, on the basis of paleoceanographic reconstructions. I think the issue is still out as to what the partition of mass was between southern hemisphere and northern hemisphere, and I really don't want to go there other than to say there must have been a reaction in the southern hemisphere, but the flux into the Gulf of Mexico, it's the only region where we have clear paleoceanographic evidence of a big meltwater spike having occurred at meltwater pulse 1A time, and where we know also on the landscape in the North Dakota region, for example, that the spillways that were actually occupied by fresh water moving into the Gulf of Mexico are actually known to be there, etc. So I think that's basically as far as I can go with that.
More questions?
There's one here.
Both will get a chance. Who wants? Ladies first. Yeah, wait.
Okay, so I know like we didn't get to talk about the snowball, but I'm looking at this graph and I'm like seeing like in the question mark snowball events, there's like hardly any carbon data at all, so I'm just like wondering what's...
This is a serious problem, yes?
Yeah, so like you say something about like what's
The
going on
further
there.
back in time we go, the more data poor we become. But there is clear evidence, of deep glaciation in the tropics at that time. I think Hoffman's evidence is really, I find it really compelling. But the question is, to me, the question has always been, does that necessarily mean that the oceans were entirely covered by thick sea ice? I think no. He thinks yes. Well,
But you like have like kind of like the dotted like data around those gaps, so I'm just like wondering what's going on.
well, I mean, of course, the uranium lead dates on zircons are the best data that exist. They come from this department, after all, right? Using the zircon dating methods that actually were developed first, actually at the Royal Ontario Museum in Toronto. Okay, but perfected certainly here in this department. But those are the dates we have available, or that were available at the time of the Halverson et al. Publication, which is from Galen's doctoral thesis with Paul at Harvard.
Okay, gotcha.
Right? So this is the problem. We move further and further back in time. We're moving into a world which is more and more data poor.
Yeah,
Right.
So it's more like reconciling different data sets from different, because
You see, what I would have argued, if I'd had the time, but I will do now, is that if you look at the reconstructions, the continent-ocean distribution reconstructions that come from paleomagnetism, I think thinking here of the Lee et al. Paper in Precambrian geology that appeared in 2007, where the Australian group, produced what I think is the finest reconstruction of the magnetic positioning, if you like, of continental fragments through time, beginning at the beginning of the Neoproterozoic, right up into the beginning of the Phanerozoic, right? And Lee's results show, and he argued this way, that prior to the onset of the Sturtian glaciation, right, when the supercontinent is clustered around the equator, prior to that time, the same supercontinental structure existed on the North Magnetic Pole. So I will argue, and Lee suggested, that original position of the supercontinent, right, could have suffered a polar wander incursion event, which would have taken it to the equator. And I say, and this was discussed in two papers that Yonggang Liu and I published in JGR Red last year, that if you did load that supercontinent close to the North Pole with heavy ice cover, right, it would itself have induced, probably, a polar wander event which would have taken the already ice-covered supercontinent down to the equator. So perhaps we're missing the boat by imagining that to explain deep glaciation in the tropics, we have to glaciate the supercontinent when it's in the tropics, right? If it's possible that we could have produced a heavily glaciated supercontinent when it was near a pole, and if one can argue, as we have done mathematically, that it's possible that that loading event could have induced a polar wander event, which would have shifted the glaciated supercontinent to the equator, then we don't really have much of a problem at all, because the glaciated supercontinent, as it moved to the equator, because of its high albedo, would have protected itself, right? Given that solar insolation was down by 6%. Okay. So perhaps we're looking at this problem in entirely the wrong way, and that's what I would have argued at the end, if I'd further abused you with.
I don't know, bringing it back to the last glacial maximum. Just to understand the full last glacial maximum, you have to understand glaciation on both poles. And you showed those very nice reconstruction of the seasonal cycle in the
Yes.
southern hemisphere.
Yeah.
Do you have anything for the southern hemisphere at the same level? Because there is a lot of debate over it.
Well, I mean, that debate has been going on for more than 20 years. I think we understand those differences. Right? That's not a problem because of variations in the seasonal cycle. Yeah.
Do we know? What about the southern hemisphere? Do we know?
It's already glaciated.
Yeah, but is there a strong seasonal cycle? Is it stronger than today? Or is it...
Well, there is a seasonal cycle, of course, right? But the landscape is such that it doesn't have the possibility of responding, to the intense summertime low in seasonal insolation that occurs in the northern hemisphere at a time when the continents are not ice covered, right? So it's a totally asymmetric situation.
But there is a big debate from the data point of view whether the seasonal cycle actually changed. There are data that would suggest there was hardly any seasonality in ice cover in the southern hemisphere since after the contact with our
That wouldn't surprise me, given that the ice cover has been fully in place for what, 30 million years. Yeah. So I mean, Antarctica to a large degree controls its own climate. Of course, under modern conditions, with the ocean warming, we're beginning to see massive ice loss, right, from the Amundsen Sea sector of Mary Bird Land, right? Pine Island Glacier region, that whole region, but that's being attacked at the underside, basically, of the ice shelf by the warming ocean, rather than from the top. Right? No, these are beautifully intricate issues, I think, that arise now more and more clearly in the climate system that force us to think deeply about the interconnectedness of things that we have managed to avoid thinking about, I think, for a long time.
A last question at home? Still there?
Let's not go back.
I was just going to ask one simple question. When's the next ice age due?
We'll never have another one because CO2 happily is high.
Well, it was already once. It went down again, which we don't know why. So, what would you say from just now?
Oh, you're
I'm
serious?
seriously asking a question without thinking without CO2.
Listen, if we had not experienced the anthropogenic spike in CO2, right? We should have already, or soon be experiencing, the onset of the next 100,000 year cycle. That's the way it works. Okay. So there are those who say we've been saved by atmospheric carbon dioxide. I'm not one of those.
Well, let's thank Dick.